Hello and welcome to this deep tech interview with TE Connectivity for Mauser. I'm your host, Stuart Cording, the electronics reporter. My first ever car was a British Leyland Princess. It was a mechanical monstrosity from the 1970s with armchair-style velour seats and chrome bumpers front and rear. I'm trying to recall the electronics in the vehicle, and the only thing that comes to mind is the AM radio. We had a cassette player too, but we installed that ourselves later on. Scroll forward 50 years and it's challenging to find a purely mechanical function in a modern car. The dashboard dials have been replaced by screens, the windows are electronically controlled, and within limits, some cars can even drive themselves. So what's changing in the electrical and electronic architecture of automobiles? What is the impact on their designs? And how are power, the signals and data reliably distributed around the vehicle? To learn about the challenges today's automotive developers face and how they're tackling them, I'm joined by Andreas Engel, Senior Manager Business Development, Global Data Connectivity at TE Connectivity. Hi Andreas, and thanks for joining me today.
Hello everyone.
So let's get straight into it. And as I mentioned, the only electronics in my first ever car was the radio. What's changed in vehicle electronics over the years?
Yes, Stuart, many things are changed over the last years, and we have some global mega trends here in place, talking about more personalized, more autonomous, more connected, more electrified, and more shared driving. This all is supported by software-defined vehicle approach. That means is in principle the car becoming in future a mobile phone on wheels. Means the software in the car will differentiate in the future the quality of the car. And this is all going along with autonomous driving. For autonomous driving, you need some sensors like cameras, LiDAR and radar, for example. With the trend to connected vehicle, for that you need to use the Ethernet in the car and you need to use antenna connections to the outside wall of the car. And last but not least, the user experience with the high resolution displays with the USB ports to connect to mobile devices in the car. That means in summary, these software-defined vehicles applications are driving really the new car architecture and all the trends in the automotive industry.
And that's a really good point, because that's the next thing I wanted to go into, because my understanding is that this trend towards software-defined vehicles is also changing the electrical and electronic architecture of the vehicle. Now, that's commonly referred to as the EE architecture, and what that's doing is it's moving us away from one feature per ECU in the car to multiple functions distributed across fewer but more powerful ECUs, sometimes even high-performance computers. Is that what you're seeing at your customers?
Absolutely. We have a change of the architecture in the next couple of years, and this is also driving the design of the components like the connectors. We had in the past a kind of legacy architecture with distributed systems. That means every function was connected to a box. Actually, the state-of-the-art architecture, it's called domain centralized. That means we have a degree of centralization and we have a kind of domain function into that, starting with some central units for ADAS and for infotainment. But in future, we will have then a next generation, a kind of zonal architecture. Every zone in the car, if it's left, if it's right, if it's in the front or in the back, has his own central electronic box, what is handling all the functionality in the car. This is then combined with some central computing system who are providing really high horsepower of electronics to the whole car electronics itself. With that, we have also to develop then the components who are connecting these zonal architecture, namely the cables and connectors. And we as TE Connectivity, we have a broad portfolio here to support that. In the past, we had the FACRA and the HSD connector systems who are dealing with data rates of 6 gigahertz and 6 gigabit per second. Now in the domain architecture, we have miniaturized coax systems, we have the MATEnet, we have the GEMnet, for example, for Ethernet application. And in the future, we are looking forward to integrate more multi-port connectors, multi-hybrid connectors, more sensor connectivity, and also some connectivity systems who are equipped for higher data rates. Is it with electrical transmission? Is it with optical transmission? This is actually open.
Now, of course, what you've just described there means that there's a need there for that continued robust connectivity between these new sensors that are being built into the vehicles, radar, LiDAR cameras, and the electronic processing that is going to deal with all that sensor data. How is the automotive system developer ensuring that the connectors used are safe, reliable, and still meet the needs of an application like ADAS and autonomous driving?
Yeah, absolutely. These ADAS and autonomous driving applications, they are generating new requirements in the automotive industry for the connector solution especially. And if you look into these applications, we have these high power computing systems. We have any kind of cameras, if it's integrated, if it's interior cameras as a satellite camera, and we have LiDAR and radar systems. All these systems have to be connected in the car. The most important one is that we implemented the Ethernet network some years ago, and this Ethernet network is then connecting all the modules, and it's connecting these high power central computing unit. This is all running with data rates of 100 megabit, 1 gigabit, but there's also a plan to run this with 10 gigabit and maybe in future with 25 gigabit per second, what generates really, really high requirements for the robustness. Also, we have these cameras in the car with a high resolution to identify the pictures and really to guide the car the right way. And this needs also powerful data lines to transport this. Actually, these data lines are with 10 gigabit per second, but we are looking forward in the future that we have also here higher data rates. More than 20 gigabits are under discussion. In addition, we need a high efficient packaging in the car because the electronic becomes, in principle, the content becomes more and more, and we have to pack this. And this is also a degree of robustness what you need here in the packaging. And we need more miniaturization of the interfaces because if we have more data ports, these interfaces are in principle defining now the space what an interface or what a device is needed, and that's why we need more miniaturization. All of that, it's going then under the requirement of automotive robustness for safety critical application. And if you look into the products, what TE connectivity can provide here, we have, for example, the MATEnet system, what is designed on base of nano MQS, what is a standard automotive terminal. That means this terminal is anyway automotive robust and full tested for automotive requirements for all robustness classes. We have the GEMnet, what is a connector for high data rates up to 56 gigabit, and what is also providing high degree of robustness. And we have the well-known coaxial systems like FACRA, for example. FACRA is since 25 years in the car. That means we can really work on this base as a very robust system. But we have also miniaturized systems like the METAX now in the car. And nevertheless, we have also camera connections in the car with fixed or floating coaxial sockets for the cameras. All this describes this world of the connectors and needs to fulfill the robustness of all these applications.
And I guess sort of the requirements are similar for other in-vehicle systems, like, for example, the infotainment system and all of its displays and consumer ports.
Yeah, absolutely. The infotainment and consumer ports needs also to follow the requirements of the automotive robustness. Here we have the same high performance computers for the infotainment as well. Sometimes these computers are combined with the ADAS computers. We have these high resolution displays. We have the USB ports and we have integrated antenna systems. And in principle, if you look into that, they are also involved in the Ethernet network with the respective data rates. But in addition, we have here this high resolution of the displays. If you look for 4K displays, if you look for 8K displays, and all the customers who are buying a car, they like to have that the display is working safely. That means if a display is not working, this is a quality issue of the car. And in addition, we have these consumer ports in the car. For example, the USB-A or the USB-C with high data rate, but also with high charging power. We have actually a power rate of up to 240 watt for USB charging port, and we have data rates in these interfaces up to 10 gigabit per second. This has to run under these automotive circumstances. The connectors we are delivering for that. To give an example, in the past, all the USB was connected in the harness over the HSD and the HSL system. This was enough for USB 2. But in the future, we are looking more forward to the GEMnet system, because the GEMnet system can transport then higher data rates if it goes to 10 gigabit, if you have to use more lanes with the USB-C. But the GEMnet is also a very good system for the future for the displays, who are actually connected via HSD, but in the future they will be connected because of the higher data rates via GEMnet.
And the other area that is obviously of ever more importance in the automotive space is the RF systems. They're integral to making sure we've got GPS signals and cellular connectivity and the availability of Bluetooth and Wi-Fi. I mean, what developments are you seeing in this domain on the data connection side?
Yeah, absolutely. And these integrated antenna modules, they are an important part of the car architecture. Some people talk 10 years about that. Can we do everything wireless? This is still not happening. Yeah, everything in the car so far is connected via coax. What is coming from the antenna signals, then over the antenna module is connected via coax lines to the central units. That means all the signals from the antennas are transported via wires. The only what is then in addition working in the car is the Bluetooth network, what is then connecting all the mobile devices to the head unit, and partly we have also WLAN, wireless LAN connectivity in. But from the connectors, the main connectors who are used for all this antenna functionality is it GPS, if it's 4G, 5G, yeah, if it's Bluetooth, all this connectivity, what is related to the harness is with coax, and we have here the products Metax and Facra, who are the typical products to connect that.
Now, the automotive industry is known for being very demanding in terms of its technical requirements, and I can't really imagine that they're prepared to compromise on all those hard-won improvements they've gained over the years, things like size, EMI performance or reliability, in order to achieve these technical advancements that they need. How does that look?
Yeah, this is exactly the challenge we are confronted every day with. Because to bring high-speed data transmission into the cars is related to some special requirements. And on top, so far, is the radio frequency, the RF requirement for high-speed data transmission. This is a special feature what has to be implemented in all these connectors. What is in principle deviating from the standard power and signal connectors if you talk about higher data rates, higher frequencies. In addition, we have these electromagnetic interference, EMI, the performance in the vehicle harness. That means, in other words, our systems are not allowed to interfere electromagnetically with other systems to disturb them. That's why we have to design our products, the connectors, the headers, the cable assembly in that way that they are fulfilling these EMI requirements from our customers. The third point, what I like to talk here about, is the miniaturization. More ports, smaller ECU space. This is really then driving the miniaturization. And if you think about that, we have maybe in the future more than 100 ports in one device. This needs really to be integrated. This needs miniaturization. A fourth point is the interface standardization. The interface standardization is mainly driven by the OEMs to ensure the quality and efficient cost. That means if you have defined interfaces globally who are following certain standards, like the US car standards, our customers can be sure that all these provided components following a certain robustness standard, certain quality standard, and they can use it right away. And finally, the global supply chain. We have to deliver in all the regions the products with the same quality, with the same performance. Is it North America? Is it South America? Is it Europe? Is it India? Is it China? Is it Korea? Is it Japan? Global supply chain, this is really here the key we have to work on to make it happen.
Now, we've already touched upon RF technology, and I can only imagine we're going to see more of this, especially as features such as vehicle-to-X communication roll out. How is TE Connectivity tackling and supporting these applications?
Yeah, in principle, we testing and simulating our connectors that way that from the beginning, from the basic design, we are doing simulations to fulfill all these requirements. This is later on then going to a kind of component level testing, what is related only to the component. And then we are testing in a system environment because it's absolutely essential that our components are working in a system environment. And that's why they have to follow certain design requirements and performance requirements. A good example of a system level test is the EMI test, what I just talked about, but there are also other tests in place to run the complete network, to run the complete functionality of the car in one architecture. And to achieve the best class in quality, we are doing always a kind of optimization here. That means if a product has some issues in the area of the frequency, in the area of the impedance, we are able to simulate that, we are able to correct this, we are able to influence the design of the product, we are able to influence the process, how the product is produced, by example, the cable assembly, and then we can also bring this in a system level simulation, and we can bring this in a system level test. With that, we can achieve really best performance beforehand, because these products, they have to work over 7, 10, maybe 15 years in the car. And this needs really to develop carefully and to be tested carefully.
Now, I also assume, and I think you sort of touched on it just before, that there's some sort of level of standardization going on so that the same types of connectors are used for the same types of applications, regardless of the vehicle manufacturer. Is that something that everyone's getting behind?
Yeah, with the standardization, Ethernet is a good example of standardization. The Ethernet standardization was started around about 15 years ago, and it was a hard work so far for the automotive industry really to transfer this Ethernet technology from an industrial and consumer area into the automotive. But meanwhile, we have several standards here in place. For example, we have the 100 base T1 dealing with 100 megabit. We have the 1000 base T1 dealing with 1 gigabit, but also looking forward to multi-gigabit standards like 2.5, 5, and 10, and in future also to 25 gigabit per second. What was done here, they optimized also the chip setup, especially for the automotive industry to save cost. They also reduced the numbers of wires who are used in the Ethernet network to make it more efficient for automotive. And with this approach, at the end, it was possible to implement typical automotive interfaces like mentioned here, like MATEnet and like GEMnet. Our special highlight for the Ethernet is the MATEnet. We especially developed this system for Ethernet. It's a differential two-wire twisted pair system, what is able to transport up to 1 gigabit per second, over unshielded twisted pair. That means for this, you need not a shielded cable. You can use an unshielded, what drives the cost down. And we are using in this system the nano MQoS contact, what is a good proven automotive contact and very robust. But under development, we have several things here in the standardization. We are looking for higher data rates, as said, but we are also looking for lower data rates. The Ethernet community, for example, is looking for solutions for 10 megabit per second. The sense behind is really to replace all these CAN bus systems who are actually working in the car and then implement or integrate the system into Ethernet to have the same software base for the whole car, for the whole system. Also, the Ethernet community is working on some high-speed gigabit over coax. What can be used in future, for example, to connect cameras and to integrate cameras directly in the Ethernet. But nevertheless, they are working also on other alternative technologies like plastic optical fiber, like glass optical fiber. And there's also a standardization now in place for 25 gigabit over glass optical fiber, what is a very interesting approach for the future.
Now, unfortunately, I don't get much chance to do as much hands-on engineering as I did in the past, but through my conversations with people like yourself, I get the feeling that design engineers are being given ever more technologies to deal with. Each technology is highly complex, and they don't have much time to become experts in every nuance and detail. What support can TE Connectivity as a supplier provide such development teams as they tackle these types of challenges?
Yeah, that's a very good question. In principle, this is the key why customers are choosing us. Yeah? These global capabilities and this global support. About the portfolio, we just talked. Yeah, we have a complete automotive portfolio. The robustness of the connectors is given, the high speed is given, the smart design is given, and we can design this in principle with every customer. It's an OEM, it's a tier one, it's an harness maker. And we can also look for full automatization, production, and so on. The global footprint, this is one of the key points. TE Connectivity in principle is active with the data team in all the regions. We have a data team in Americas, we have a data team in Asia, we have a data team in EMEA, and we have productions all over the world. But just to give you, let me say, a hint, we have around about 100 engineers all over the world working especially for these connectors. But we have production places in Mexico, we have production places in Morocco, we have production places in Central Europe, we have production places in China. Yeah, all these organizations can in principle support from the knowledge point of view, from the production point of view, and also from the automatic process point of view. And nevertheless, the experience and the expertise in this area is also very important because our customers can trust our engineering designs. They can get samples, they can get prototypes. We can do the lab testing by self. Even not only the lab testing, we can also test during the development of a product. That means we have also development labs for that in place. We can do simulation of our products. And for sure, we can do all this complete automotive robust validation process, what is so far specified in this harsh environment of an automotive area. And we have also development collaboration all over the world, really to bring the best knowledge together and to provide the best support for our customers.
Well, it's been a great overview of the portfolio, firstly, of the automotive connectivity and connectors that are available from TE Connectivity. So thanks for all your insights there. We've actually been out to our community and asked them to provide some questions that they might have. And I'm just going to turn over to some of the questions we got in. Now, this is something that you already talked about a little bit on terms of simulation tools, but I think some people are sort of the frequencies of these signals are getting so high now. it's very difficult, I think, to maybe get the PCB design right first time, or even second or third time in some cases. Can you go in a bit deeper on the simulation environments that you support? Are these third-party tools or are these in-house tools? And how do you support your customers through that design process of their circuit boards?
Yeah, for sure. We can support the customers with the design and of the products. We have some state-of-the-art tools available. It's, for example, ST Microwave Studio or HFSS von ANSYS. Yeah, and these global tools who are working in the environment of a CAD system, they can in principle help then our designers and also the designers of the customer to find the right solution for their implementation of the connectors to the board and to the integration in the electronics.
Super. That's a great starting point for those that are struggling at that stage in the development process. And next question actually comes right back to the beginning, I think, right back to the starting point of many designs, is how do I find the optimal connector for the application I'm running? Are there some sort of selection tools available, or how do I go about finding what's the right connector for my application?
Yeah, that's very easy. Please go to the TE connectivity homepage. You can select there for data connectivity connectors, and then you can choose differential connectors, coaxial connectors, hybrid connectors, all these different portfolios and families of the connectors. But if there's a technical problem, please give us a call, ask us, we will help.
Fantastic. Right, so there's a little note for everybody there. Another question that came up, and this is something that I've had to deal with in the past as well. I mean, often you're doing a prototype construction, and you need to obviously put the connector on and attach a cable to that connector as well. And I've seen in many documents for connectors, there's often a link to be able to buy or source some specialized crimping tools, because you can't make these connectors by hand anymore. What do you do in that there to help people, maybe with, I don't know, the crimping tools or something that people can use, and then how do we move from that prototyping process into mass production of those cables and connectors that we need?
Yeah, this is really a good question. And I remember 25 years ago, it was all possible to do with crimping tools, with hand tools, and so on. Even we had at this time crimping tools for plastic optical fiber. But now with increasing the data rates more and more, it's necessary to have a certain quality of this production. And that's why we are producing then for the customers pigtails, or we are producing cable assemblies who can be used then for testing. But if you look, for example, towards the MATEnet system, what is consisting out of cable assemblies with nano MQS contacts, there's still possible to buy a crimping tool for the nano MQS contact and to assemble that according to a certain specification. Yeah, but the majority of the systems, to be honest, now has to be produced really in a qualified model shop, so to say, with automatic or full automatic lines to support the quality. But if there's any help needed regarding prototyping, we can still discuss this, we can go in contact, and we will find a solution.
Fantastic. That's great news, I'm sure, for people who are wondering how they're going to overcome that challenge. Now, there's one more question here from our audience, and this is an interesting one for me as well, because we've talked about lots of different types of connector, and there's certain types of connectors that are well suited to Ethernet, well suited to RF, well suited to maybe handle the lower data rates like CAN and things like that we see in the vehicle. And we're talking also a lot about standardization with software-defined vehicles and these domain architectures. Are you also seeing any sort of move to like a standardized connector that has standardized positions for power, for signals and data?
Yeah, that's in principle the next step we have to do, really to implement such kind of, we call it hybrid connectivity. modular hybrid connectivity into these ECUs, into these central units, because we have so many data ports in there that needs really a kind of miniaturization, centralization. We have several systems here to offer. One of the most popular system is the NetAx Plus. NetAx Plus in principle can integrate coaxial ports, differential ports, signal ports, what means relatively small pins for signals, and also power pins. And with that system, then you can really shrink down the space of the connector, and you can efficiently integrate this into the device. That means this is really the new trend to tackle this, also to talk in an early phase with the harness maker to find the right routing of the cables then afterwards in the harness, and to combine this really in a consolidated hybrid connector.
Well, that's great. Thanks ever so much for all those deep technical insights, Andreas. I think we've learned a lot and have a much clearer view of how we're going to tackle the connectivity challenges and the connector challenges in the next generation of automobiles.
Thank you very much.
Well, that's all we have time for, so let's review what we've discussed. The EE architecture of the automobile is undergoing massive change, requiring the transfer of huge quantities of data while conforming to existing reliability and safety standards. This demands a selection of appropriate connectors that meet them while supporting the integrity of megabit, gigabit and even RF signals from the prototype in the lab right through to the production vehicle that may be on the road for decades. TE Connectivity offers an extensive portfolio of connectors that make it possible to design and implement these next-generation in-vehicle networks, covering everything from multi-gigabit differential signals and miniaturized coax right through to automotive Ethernet and more. My thanks go to Andreas Engel of TE Connectivity for sharing his technical insights on the changing in-vehicle connectivity environment. And if you'd like to explore the connectors suited to these types of applications in more detail, follow the link to the Mouser website.